the first example, we have an op-amp that's an amplifier. It has a supply voltage of plus minus 5 volts and the gain of 20. So we're going to sketch the input wave from the output form. So this is the output form. So it looks like it's in the linear range. It didn't get into the saturation range, right? If it hits the saturation range, the output should be either positive 5 volts or negative 5 volts. So since we know the gain is 20, so the gain is defined as the ratio of output and input, the output over the input. So the input will be equal to the output divided by the gain. So we know that the input will of the same form, but it will be 20 times less. So the input will be something like this, but it's 20 times smaller. So the peak over here is no longer 3, it will be 3 over 20. And similarly, the others will be 2 over 20 and 1 over 20. And the same thing on the other side. It will be a negative 1 over 20, negative 2 over 20, and a negative 3 over 20. And part B, double the amplitude of the result in A and sketch the new output. Double it as new input, so this will be 3 over 10, this will be 20 over 10, this will be a 1 over 10, similarly here, negative 1 over 10, negative 2 over 10, and negative 3 over 10. So this is a new input. Given this input and we want to find the output, we know output is equal to the input times the gain. So we know that Vi is of this form and G is 20. So we time 20, this time 20 will be 6, and this will be 4, and this will be 2. So negative 2, negative 4, and negative 6. So if it's in the linear range, we should get this result, right? Let's check if it's still in the linear range or not. So we know that the power supply has a range of plus minus 5 volts. So the maximum output should be between 5 volts and negative 5 volts. So we know that it won't be able to reach 6, that it enters the saturation region. So we need to revise this. So you don't want to be able to come over here. You can only go up to 5 volts. It will maximize out at 5. So second question, we're going to use the ideal op-amp model to determine the voltage gain of the circuit. So given this circuit, we want to find out the voltage gain. The voltage gain is defined as the ratio of VO over V1. First step, so this is something I encourage all of you to do, is to basically say you're going to use the ideal op-amp model for analysis. Then you define your nodal voltages and the current I plus and I minus. So this is our current I minus, and the other one will be my current I plus. So both of them are defined them as the current goes into the op-amp. And at the same time, I'm going to define this as my nodal voltage. So it also means that I'm going to define a reference node. I'm going to define the node as a reference node. So I will define this as my reference node. And I will define this node have a nodal voltage of V minus, because we call this node as an inverting terminal, and it has a nodal voltage of V minus. And the other node have a nodal voltage of V plus. So I define my nodal voltages, and also the currents goes into the op-amp. And I know that if I use ideal op-amp model, V plus is equal to V minus. At the same time, the current I plus is equal to I minus is equal to 0. So these are the two conclusions that we have for ideal op-amp model. The second step, I'm going to write a KCL equations. Which node are we going to look at? At the non-inverting terminal, we write the current that goes into the node that is equal to the current leaving the node. The current that goes into the node, so from this branch, which is 0 minus V minus divided by 1K. The current goes from this branch into this node, which is VO minus V minus divided by 20. That is equal to the current leaving the node. We define it as I minus. At the non-inverting terminal, what do we have? Non-inverting terminal is over here. And we know this nodal voltage already. We know that V plus is equal to V1. That's how we get all the equations. The rest is to solve the equation. Step 3, we're going to solve the equations. So from here, we already know that the current I minus is equal to 0. So the right hand side is 0. And the left hand side, V plus is equal to V1 and V plus is equal to V minus. So we can replace V minus by V plus and then further by V1. So this will be our V1 and this will be V1. And the right hand side, that is 0. So this is how we simplified it. VO over V1, that is equal to 21. In the next example, we have two signals that are connected to two different terminals of this op-amp. And the output is VO. Same thing like what we did before. The step 1 is always to state that we're going to use the ideal op-amp model for analysis. V plus is equal to V minus, I plus is equal to I minus is equal to 0. So this is how we define the nodal voltages and also the reference node. We select a reference node to be there. And step 2, write the equations. At the inverting terminal, we have, this is 6 volts. So 6 minus V minus divided by 1. That is the current goes into the inverting terminal. The current goes into this node through this branch, that is VO minus V minus divided by 4. And the current leaving the node is I minus. So this is the equation that we get at the inverting terminal. At the non-inverting terminal, V plus is equal to 2 volts. Right? That's all the equation that we have. So step 3, we're going to solve the equations. To solve the equation is also pretty straightforward. The right hand side is equal to 0. And the left hand side, we have a V plus is equal to 2. And a V plus is equal to V minus. So we can replace V minus by 2. So right hand side 0. And replace the V minus by 2. Then we can find the output VO, negative 14. So the last example that we have is a little bit more complex. So this is a design example. I have an op-amp amplifier. It operates with a power supply of a plus minus 15 volts. Can output no more than 200 milliamp. And what is the maximum gain allowable for the amplifier if the maximum value of a VS is equal to 1 volt? We want it to operate in the linear range. If the maximum value of the input is equal to 1 volt, we don't want the gain to be more than 15. If the gain is more than 15, then this will be in the saturation region. So that is some information we can get from these two pieces of information. Another piece of information will be R1 plus R2 is equal to 10 kilo ohm, assuming that we have this. So this is another requirement. Step 1, from the definition of amplification gain, we know that the maximum gain G should be less than 15. The output, which is the power supply, 15 divided by the maximum VS, which is equal to 1. So from here, we know that it should be less than 15 from the first requirement. The second requirement comes from the output current no more than 200 milliamp. So let's see how we calculate the output current. We know that for ideal op-amp model, the current over here in this branch, this is my current I minus. What is I minus?
0.
I minus is equal to 0, right? In calculating the output current, I can assume there is nothing going on over here. You can treat the whole thing as nothing there because that current is equal to 0. We only care about the output end. This is the output VO over here, right? Then we can calculate the current. The current in this branch, which is VO divided by 50. And the current in this branch, that is VO divided by R1 plus R2. So we know that this current should be less than 200 milliamp. Let's use a standard unit. If R1 plus R2 is equal to 10 kilo ohm, so replace this by 10 kilo ohm because we use ohm. This 50 is ohm and everything is a standard unit. So then we can find the range for VO. So VO should be less than, the first term is much larger than the second term. So we can drop the second term. So that will be, VO will be less than 10. So we can find the amplification gain should be less than VO divided by the maximum of 1, which is less than 10. So from the second requirement, we find the amplification gain should be less than 10. And step 3, able to draw the conclusion by combining the two together. We find the maximum amplification gain is equal to 10.